is the weakest base. And the strongest conjugate acid here is the chloride ion, is the strong acid. Yeah.
How come everything has the same KW? 1 times 10 to the negative 14.
Because when we look at this chemical equation, water is releasing hydrogen to act as an acid. So its K for releasing a hydrogen is 10 to the negative 14. Its K for releasing hydroxide is also 10 to the negative 14. That's why water is an oddball. There's nothing else that releases both hydrogen and hydroxide in the same amount.
How come they all have like 10 or 1 times 10 to the negative 14 though? There's like different things, different compounds, different acids. Use the same.
You mean why do we use this for all of them?
Yeah, why do we use the same value for KW?
No, because KW refers to just that.
Yeah, all these acid-base things that we're doing, all these considerations of acids and bases, are all in aqueous solutions. They're all in water. So any acid that you put into water is going to raise the concentration of this thing. And if you raise this, according to Le Chatelier's principle, if we add more hydrogen, what's going to happen to this equilibrium?
More water.
Goes back this way. And what happens to the amount of hydroxide then?
Goes down.
It goes down. So if you raise the amount of hydrogen, you'll always decrease the amount of hydroxide. So acids and bases are always messing with that equilibrium. So everything comes back to how much hydrogen is in the water or how much hydroxide is in the water according to that equilibrium. Did I do okay on that? Does that make sense? So everything is kind of revolving around the KW. And KW holds everything together. Okay, I'm getting a little bit nervous now about running out of time. I'm going to go through this real fast and watch it on the YouTube again if you don't get it. Okay? I'll try to explain it, but you can't ask any questions now. Because I still need to talk about polyprotic acid. When you have an acid that has 2 hydrogens in it, or 3, what do you do for that? But I'm going to abbreviate that. Let's do this very quickly. Just like the reading quiz, water, is it acidic, basic, or neutral?
Neutral. Or both.
Right, it's got the same amount of hydrogen and hydroxide in it as long as it's pure. It's neutral. Sodium chloride. Emily, this is your chance to redeem yourself. Huh? Sodium chloride, acidic, basic, or neutral?
Neutral.
Also neutral because sodium is neutral and chloride ion is neutral. It's not able to act as a base and take a hydrogen. Oops. What about KNO3?
Neutral.
Neutral.
HNO3 is a strong acid. Therefore, the NO3 ion is not able to take a hydrogen. Is neutral. K ion is neutral. KNO3 is also neutral. So neutral, neutral, neutral. Can we do this forever? No. NaNO2. Yes?
Basic.
Why?
Because. It's from a strong acid.
Right. The nitrite ion, NO2, is one of these negative ions. I told you this yesterday. It bears repeating again. I gave you a replay on it yesterday. I told you twice. Here's your day after replay. The conjugates of the 6 strong acids are neutral. All other anions are basic. You got that? All anions are basic except for those 6. So that means that thing right there is a base. And what about Na? Is that acidic or anything? No, it's a neutral ion. So yeah, NaNO2 is basic. If I have sodium nitrite, NaNO2, solid, I put it into water and stir it up, I'll see that the pH goes up. It's basic. That NO2 ion is going to pull some hydrogens off of some water molecules and increase the hydroxide concentration. NH4Cl, what's going on there? Acidic. The chloride ion is neutral, just like that chloride ion was neutral. But the NH4 ion is what? It's an acid. It's got an extra hydrogen on it. It's an amine that has taken a hydrogen. What's the amine that has taken the hydrogen to make this?
H3.
NH3, ammonia. I guess it's not really an amine because amine has to have carbon in it. But the ammonium ion is definitely acidic. It's the conjugate acid of ammonia. No questions? Good. I have 2. I have give the pH of sodium cyanide and then give the pH of ammonium chloride. I think I'm going to choose this one The one before, the sodium cyanide. Elaine, you still get your book open? Okay, keep it open for a moment. Is this acidic or basic?
That is basic. Basic. Yeah. Basic.
Basic is right. Basic. The sodium ion doesn't do anything in water. The cyanide ion is basic. It's not one of the 6 conjugates of Strong's. All right, so if it's basic, can you write a chemical equation for what happens when you put cyanide into water? What is the job of a base? To take hydrogen. Where does it get a hydrogen from? There's no hydrogen in here.
Water.
It gets it from the water. Right. So for a base, it's got to have water as one of the reactants. Go ahead, take a moment, write the chemical equation. Leave the sodium out. Sodium is a spectator doing nothing. So just leave it out.
Oh, yeah, okay.
Yes.
For the quiz in the past, do we have to like write like the states?
No. No, you don't.
So in the quiz, should we also leave out the NA? Like if we're getting to
Yes,
just
leave the
it
NA out. Just like in
You're right.
chapter 4, the NA is not doing anything and leave spectators out. Now, when you have yours done, I'm just going to uncover mine and see if we have the same thing. You got that? Sometimes for some of these problems, the worst thing in the problem is writing the chemical equation. When we do the next chapter after exam week, the buffer chapter, those chemical equations, it's going to get you. Emily?
Do you need to write this physical states?
No.
Dude, I just asked that.
Oh, you did? Sorry.
Maybe she needs some tutoring, Nabil.
I think she does.
Maybe
Charge
you
the
need
premium.
some lab help.
Okay, so I'm laughing because I know what's true. We know what the concentration of the cyanide ion is, so we can make an ice table. And let's go ahead and do that. There's my Kw equals Ka times Kb. I knew it was in here somewhere. Okay, we have started the ice table with our initial line, and so let's go ahead and complete this thing. The reaction is going to shift to the right. That means that on the left side it's going to go down by some amount x, on the right it goes up. So we have 0.1 minus x on the left, x and x on the right. Now over here, I'm just going to put down what the Ka of HCN is. But we had that before too, Elena. Do you remember what it was?
Yeah, 6.2 times 10 to the negative 10.
Thanks. Remember, this is a base, but we don't have cyanide in our Kb table. So we have to be resourceful and figure out what the Ka of the conjugate acid is, and then figure it out. That's why I gave you this reminder. Yeah? All right, so let's go ahead and do the math. We need the K for this reaction, which is going to be the Kb, because this is a basic reaction. It's going to be Kw divided by Ka of HCl, which is 1 times 10 to the negative 14, over the Ka 6.2 times 10 to the negative 10. That is Kb. Kb is equal to the product over reactant concentration. So that's going to be equal to x squared over 0.1 minus x.
This is 6 or
Which one? This is 6.2.
what's the top one?
Oh, what happened to my...
Like 0.
The question is, what is the pH? So we need, we don't have a hydrogen concentration, but we do have the hydroxide. So if we find hydroxide, then we have to go through the, get the POH, subtract from 14, find the pH. Yeah? Easy enough? All right. So let's do the math. Can we use the 5% rule on this one? Looks like our K value is 10 to the negative fifth. Yeah? Leave out that minus x term. What do you get for x? X, which is the hydroxide concentration, is, can I have somebody do that and yell it out?
1.27 times 10 to the negative 2.
Okay, just to save room, I'm going to say 0.01. Can I just put 1, 3?
Wait, did I?
Oh, 2 zeros?
2 zeros. Yeah, 2 zeros.
Okay, and that's molarity, that's the hydroxide concentration. So take the negative log of that, that's going to give us a POH. And then subtract from 14, let's just jump right to the pH. This is real close to a POH of 3. 0.001 would be 3 for its POH. And subtract that from 14, it should be around 11. 14 minus 3, 11.1. Anybody have any questions about that? No? So you'll have things like this where you're given a salt solution and you have to figure out what its pH is. Yeah? Matthew, I don't know if I can answer that question.
Did we do 1.0 times 10 to the negative 14 over like 6.2 e negative 10? Did we do, is that kW divided by Ka?
Yeah, what happened? I must have erased it accidentally. Yeah, it was Kw divided by Ka.
Okay.
Yep. To find the Kb of the cyanide ion. Yep, done. Good. All right, here's my last thing, and I'm going to do this fast. I'm going to put this up for a moment. Now, when you have a polyprotic acid, the prot in the middle of this thing, prot represents proton, which is nothing more than a hydrogen ion. That's all a hydrogen ion is a proton. Hydrogen, one proton, one electron around it. It loses its electron. That's kind of a bummer. That's what makes an acid acid. It's a silly proton. So a polyprotic acid is one that's got multiple hydrogen ions in it, like H3PO4 or H2CO3 or H2SO4. Those are polyprotic acids. We think that in polyprotic acids, the hydrogens all don't just start falling off all at once. They seem to come off very systematically, and we have an actual K value for each hydrogen that comes off. That's what you saw, Elena, in the table there. You had Ka1 and Ka2 for that diprotic acid, because we have a different K for each one. Now, we do treat each of the hydrogens individually. When we have H3PO4, you got this structure that has all of its hydrogens on it. The first one comes off, and the first one is always the one that comes off the strongest. The first hydrogen will always be the one that comes off strongest. And this is a pretty healthy Ka value. 10 to the negative third is a good acid. I mean, this thing is going to release a lot of hydrogens. Once the first hydrogen comes off, now we're left with this, H2PO4. It's got one of its hydrogens taken off. Now that one is going to try to lose a hydrogen. So it is going to serve as an acid. And as it loses its hydrogen, notice the effectiveness of this acid goes way down. Ka2 is about 100,000 times weaker than Ka1. Look at that order of magnitude. 10 to the negative third goes down to 10 to the negative 8. This always happens with polyprotic acid. The first hydrogen comes off way stronger than any of the other ones. This started with 3 hydrogens. It still has one that it can get rid of. How's that one going to come off? Even worse. It's going to come off even harder than the others. I'll just go ahead and uncover that. Now just with one H, the HPO4 negative 2 ion, releases that third hydrogen. Look at that, K. 10 to the negative 13th power. It's terrible for trying to release a hydrogen. In fact, these two ions are pretty good at being bases, in honesty. Some of you are in GBBE, best days of your life probably. The GBBE often will use phosphate buffers, where you'll have some H2PO4 and HPO4 mixed together, so you got a little bit of acid action in there and a little bit of base action in there. That's what we're doing next is buffer system in here. All right, now because the first Ka that came off was so much more effective at releasing hydrogen than the other two, when we have a polyprotic acid and we need to find its pH, this is the part that you need to know. Just use the